Now that we know how to make models through this process of deconvolution and weighting, we can go on to the next section, which is self-calibration. This ties back to our series on calibration in the following way. Well, let's recap our basic calibration strategy. The way we do calibration is to transfer solutions that are derived on very simple, very bright point source-like fields onto a piece of field that we are interested in doing science, right? Our target field. Now, we can still have phase variations between our gain calibrator scans in this target observation. So things like the ionosphere will add phase variations to our visibilities, along with things like changing cable delays and so forth. Now, I particularly state phase variations here because that is predominantly the biggest source of remaining calibration error if we have an array that is temperature stabilized, such as Meerkat. Now, if you look at the graph here on the bottom right-hand side there, the graph shows the accumulative divergence in visibility phase from a state where it was calibrated, right? So at time 0 there, we've fully calibrated our array, both in amplitude and phase. And then as we observe for longer and longer, the phase starts diverging from this state. So this primarily stems from ionospheric phases and from remaining systematic issues. So in order to now calibrate out residual sources of error between these gain calibrator scans, we need to go through this process of self-calibration. Well, what do I mean by self-calibration? Well, it's really quite a circular argument, but it works. And we'll see why. Now, the process of imaging starts off, of course, with our transfer calibrated visibilities, right? So we've solved for the calibration solutions on our calibrator sources. We've interpolated it across our target field, and we derive an image and deconvolve it to get a basic model of that field out. Now, instead of using just a point source model as we had for our calibrator field, we use now this model that we derived through this process of carefully deconvolution and perhaps also constraining the deconvolution to only the brightest sources in the field. In the practical session, I will show you how to mask, as we say, such a deconvolution process. But for now, we can just take our model from this deconvolution process, we plug it back into exactly the same solver routines that we've already developed for our calibrator source, and we calibrate the temporal effects on our system gain even further with this model. So essentially, we're calibrating the visibilities to a model derived from themselves. So we apply those solutions that we derived, and we go back into imaging and deconvolving further. So typically, this will systematically improve the image quality, and we can go deeper and deeper and deeper in our deconvolution to capture more and more flux, right? So one strategy that I would suggest that you use is to maybe start off with phase solutions at very long intervals during our target scan. So let's say 2 or 3 times during a 20-minute or so target scan, and just derive a initial correction. In this way, if you've missed some low-level flux in the image that you started off with from the transfer calibration process, at least you wash out most of that flux and don't absorb it into the solutions. Now, as this the calibration errors around the sources go away, you can steadily build up a more fine-grained model of your target field. Now, of course, this process is going to be limited by our deconvolution algorithm. So if we have very broad-scale extended emission that we can't really model that well with just the normal Hoogboom-Kleene algorithm, our calibration in the end will also be limited by that. So one has to be careful when you do this, to capture as much flux as possible without capturing the side lobe structure from calibration errors. So now that we've seen the process behind self-calibration, let's look at an example here. We're in the galactic plane here, so possibly the worst possible place to try and deconvolve using just the Hoogboom-Kleene algorithm. However, it still does a substantially good job, even with its limitations. Now, the image on the left-hand side there, as you can see, has a lot of side lobe structure left in the image. Now, that is because the true instrumental response with all these temporally variable gains differs substantially from our idealized PSF response. So we're not able to deconvolve out the response of the instrument. So by systematically building up a model through this process of iterative calibration and imaging, we can derive very fine scale solutions in time to describe the phase variation induced by the system and by the ionosphere. Now, you'll see that the image on the right-hand side is substantially improved. And this is the final image that we got after many rounds of self-calibration. You'll see that the side lobe structure on the more compact H2 regions within this field is substantially reduced, and the image quality has substantially improved. So, to recap, what we do is we image, we calibrate, and we repeat. So, and we have to do this multiple times in order to get our final science image out. All right. So these effects can also be direction dependent. In the case that we pointed out just now on the galactic plane, we didn't do direction dependent calibration or applying direction dependent corrective terms. We simply applied the same gain to all parts of the sky, right? So this same kind of like electronic gain solution that we derived. Now, if we look at more complicated effects, such as that introduced by the far field response of our antennas, the effect can be spatially variable, time variable, and frequency variable. So let's consider a VLA observation of a calibrator field 3C147. We're looking at free off-axis sources that is well within the first side lobe of the antenna response. On the left-hand side there is a lot of structure introduced by the variability of the antenna response that is not calibrated or not corrected for. On the right-hand side, we have applied corrective terms. Now, because the VLA antennas are alt-as mounted, the sky will rotate as a function of parallactic angle around the axis that points towards the phase tracking center in the middle of that usually corresponds with the middle of our pointing center. Now, this will effectively rotate the antenna response over the source. So if you have a variable structured response that is induced by the mounts that is holding up the subreflector above our receivers, we can see that side lobe structure is going to become temporarily variable, and so it will vary over the source as we observe. Now, This kind of variability will decouple our model PSF from the true instrument response as a function of where we're looking at in the image. So it's clearly a directional dependent effect. These effects are not seen near the center of the image, at least not such strong effects introduced by the beam. So once we've taken the beam into account through a process of faceting here, you can see the corrected image on the right-hand side. The side lip structure is both reduced in the total intensity and Stokes V images. So remember that most AGN have very little circular polarization. So any circular polarization that we see is most likely stemming from systematic effects. This is only true really for AGNs, but as they dominate the sky at centimeter wavelengths, they're going to be the dominant. They're going to show also the dominant systematic errors in the images that we create of our Stokes V or circular polarization. So looking at direction-dependent calibration, here we saw for all the terms that are unknown, that are affecting only portions of the sky. Now let's look at one particular way of doing this. Let's look at the terms in this equation. So these GFP and G and Q refers to the electronic gains for antennas P and Q for an arbitrarily selected pair. These terms affect all of the sky equally. The terms delta P and delta Q in the center of the equation refers to gains that only affect portions of the sky. So you can see that we take a Fourier transform of a model in a certain direction, right? So remember that we go back to the visibility space through a Fourier transform. So if we take just a model of a certain patch of sky that is affected by direction-dependent calibration terms, we can apply these corrective terms to correct the visibilities just in that patch of sky. We do this over all such patches which we've identified in this sum, and by constructing our error function in this way, we take into account both the model that is stemming from the sky that is not affected by direction-dependent calibration errors, and those patches of sky that dominates our direction-dependent calibration error artifacts, and while we're solving for our electronic gains. So the visibilities here for these patches are, in this case, either predicted through faceting or through direct Fourier transform of the model components within a region, or just maybe a single component that's causing us problems. Now, let's take a look at an example of how this improves the image. Starting at the top there, we're starting with the just one round of phase calibration after we've made an image of our transfer calibrated visibilities. As I said, we iteratively improve the electronic phase of the system up to a point where we're starting to get dominated by errors around particular sources for an extragalactic field like this. The only way to get rid of those artifacts now is to solve for direction-dependent calibration solutions. And we apply them and we peel off, so we subtract the corrected corrected model out of the visibilities within that patch of sky. So you can see that the side lip structure around that particular pesky source is substantially reduced by doing this. And furthermore, the interplay between our electronic gains and our direction-dependent gains can be compensated for in this case. So you can see that the overall model of restored image of the sky is substantially better than it was with just direction-independent calibration. Now, the key here is to watch out in the way you're constructing your error function here. For this observation, we have a pesky calibrator source sitting out just above our target field. And as that source moves through the side lobes of our primary beam, remember that the primary beam scales as a function of frequency again, the artifacts around that source can be really dominant in our target observation, right? We're trying to look at targets at the center of the observation, and we clearly see a lot of interference there. Now, if we peel that source through this process of direction-dependent calibration, only using a model of that source and neglecting all the flux in the rest of the field. So if we just go back to our equation there, and we only saw for the direction-dependent calibration terms that are delta P and delta Q terms, and we neglect PQ of the rest of the sky completely, then we end up absorbing a lot of flux into these gain solutions that we derive. If instead we include the flux of the rest of the sky and just solve for a solution that applies to only that particular source, we can see that we have substantially less absorption in our image. So we have to be very careful in the way we construct these error functions in a way to limit, firstly, the number of degrees of freedom to only regions of sky where there is problems, and to include as much flux as possible. Right. If you have any questions, then please contact me on my email address, bigo@ska.ac.za. Thank you so much.